In its simplest sense, ion channel gating is the opening and closing of ion channels in a cell membrane to let ions cross the membrane. To illustrate the concept, imagine the ions behind a fence. They want to cross to the other side but can't find a gap large enough to pass through. They are prevented from crossing and remain on the far side. But the fence has a gate, and when it's opened, the ions have a clear route to pass through to the other side. That is effectively what ion channels do. They act as a gate to control the flow of ions across an otherwise impermeable membrane. To understand how ion channels behave in cells, you need to appreciate that they can exist in different kinetic states, which are different conformations of the channel that dictate when ions can flow. Using an idealized version of a channel, this cartoon illustrates the different kinetic states that a channel can adopt. Starting at the top left, in most cells at rest, ion channels are closed or in the resting state. In this state, the pore is constricted, preventing ions from flowing through. In the open or activated state, the pore is dilated, allowing ions to flow freely through it. Ion channels can adopt a third state known as an inactivated state, a refractory state, or a desensitized state if it is a ligand-gated ion channel. In the inactivated state, the channel is still open, but a conformational change in the channel protein results in blockage of the pathway through which the ions travel, so ion flow is prevented. The closed and open states of a channel can interconvert, with rates depending on the conditions around the channel, such as the membrane potential or ligand concentration. In a resting cell, the forward rate is very low and the backward rate high, so that most channels remain in the closed state. When a stimulus is applied, such as membrane depolarization or the binding of a receptor ligand, the rate of the forward reaction increases, so that at equilibrium there are more channels in the open state. For a voltage-gated channel, sustained depolarization can push it towards the inactivated state. Ligand-gated channels can also inactivate during sustained ligand binding. This is a one-way reaction, so channels will remain inactivated until the stimulus is removed. The channel will then gradually recover to its resting or closed state, ready for the cycle to start again. There's more than one way that an ion channel can become inactivated. Two processes have been identified and are known as N-type and C-type inactivation. N-type inactivation involves part of the N-terminus of the channel protein, which plugs the pore, as illustrated in the kinetics cartoon that I've just shown you. C-type inactivation involves a change further up the pore, in the region of the selectivity filter, a part of the channel structure that determines which ions can permeate. This stops even the normally permeant ions from passing through. A property of ion channels that can be hard to get to grips with is rectification. The term is derived from rectifiers in an electric circuit. You make use of rectifiers every time you charge your tablet or mobile phone. The electrical supply at a wall socket is AC or alternating current, where the current continually alternates between positive and negative. But handheld devices operate on constant current, that is DC or direct current. Rectifiers are devices that convert AC to DC so that the current flows in only one direction, positive or negative. In a rectifying ion channel, current flows better in one direction than the other. Although the preference is not absolute, channels usually allow some ion flow both ways, but it is much more effective in one direction. Most potassium channels are outward rectifiers. That is, they preferentially mediate the flux of potassium ions from a cell. There are several reasons for this, but it boils down to the voltage dependence of channel gating and the reversal potential for potassium. In physiological conditions, most voltage-gated potassium channels are closed at the resting potential of a cell. The cell must depolarize for voltage-gated channels to open, and when they do, the electrochemical gradient for potassium drives the ions out of the cell. However, there is a class of potassium channel that behaves as an inward rectifier, with potassium preferentially flowing from the outside to the inside of the cell. These channels open and close independently of membrane potential, but membrane potential affects how they conduct potassium ions. At potentials negative to the equilibrium potential for potassium, potassium ions freely flow through the channel from the outside to the inside of the cell. On the other hand, as the cell depolarizes, binding sites are revealed on the cytoplasmic surface of the channel, which attract positively charged ions like magnesium and polyamines. When these ions occupy the binding site, they obstruct the flow of ions, and as the cell continues to depolarize and the interior of the cell becomes more positive, the positively charged ions are repelled and pushed towards the channel, increasing binding to the channel and further impeding ion flow. At negative membrane potentials, the opposite happens and the block is relieved. So, to summarize, potassium current is inward at negative potentials, but impeded upon depolarization. I hope you found my explanations of channel gating helpful. Thank you for watching.